Good morning, everyone, and thank you for being here. Today, I want to talk about something that sits quietly underneath almost every smart building system, but rarely gets discussed in environmental terms: the database itself. Our study asks a simple but pointed question. When you store camera images inside a database, does it matter for your carbon footprint whether you choose a document-oriented engine like MongoDB or a relational one like PostgreSQL? This is joint work from Pradita University, presented here at the 10th International Conference on Applying New Technology in Green Buildings. And over the next few minutes, I'll show you that the answer is more surprising than you might expect. Here is the path we'll take together. I'll start with the motivation, explaining why storage is fundamentally a sustainability question and not just a performance one. Then I'll walk you through our approach and experimental setup so you can trust the numbers. After that, we'll get to the results, which are the heart of the talk. And finally, we'll close with a discussion of what it all means and some practical guidance you could take home. Let's begin with the motivation, why we cared enough to run this experiment in the first place. Picture a modern smart building. Cameras all over it are capturing images, from full HD up to 5K resolution. And these images arrive continuously as a time series, each one tagged with a timestamp. That data tier runs 24 hours a day, 7 days a week. So every joule it consumes is operational carbon that keeps accruing for the life of the building. Now, when engineers decide how to store those images, they typically reach for one of two general-purpose databases, and these two have genuinely opposite designs for handling a large binary payload. PostgreSQL, with the TimescaleDB extension, uses a mechanism called toast, the oversized attribute storage technique, which pulls large binary values out of the main row and stores them in a separate location, out of line. MongoDB does the reverse. It keeps the image in line, right inside the document, encoded as BSON binary data, sitting on the WiredTiger engine with snappy compression. The frustrating thing is that existing time series benchmarks almost always use tiny numeric payloads, like a temperature reading, and they report nothing at all about energy. So our research question is concrete. What is the carbon footprint of storing images inline in PostgreSQL versus MongoDB across a range of camera resolutions? And which engine is actually the greener choice for monitoring a building? The message here is that choosing a storage backend is a sustainability decision, and it deserves to be measured as one. Now that we know why this matters, let me describe how we built the experiment and what we control for. The core of our design is a controlled comparison of two architectures where only one thing is allowed to differ. On the PostgreSQL side, each record is a row holding the metadata plus a pointer, and the actual image is pushed out of line into toast storage. On the MongoDB side, each record is a document holding the metadata, and the image lives inline as bin data right there inside it. Everything else, the workload, the hardware, the queries, is held constant, so any difference we observe can be attributed to the storage engine and nothing else. The workload itself is deliberately realistic. We use 4 resolutions from 1080p up to 5K as quality 90 JPEG images ranging from about 0.8 to just over 5 megabytes each. For each resolution, we push 2,000 records in batches of 50, and we repeat the whole thing 5 times for inserts and 5 times for retrievals, so the numbers are stable rather than lucky. We also define storage amplification as the on-disk size divided by the raw payload size, which tells us how much overhead each engine adds. And critically, both databases are wiped and rebuilt between resolutions, each with a compound index on device and timestamp, so no leftover state contaminates the next run. Let me say a word about the measurement environment, because credibility rests entirely on getting this right. Everything runs on a single host with an Intel Core i9-11900H, 31 gigabytes of RAM, and a fast NVMe solid-state drive, and both engines run inside Docker Compose, so their conditions are identical. To measure energy, we don't guess. We read Intel RAPL, the running average power limit counters built into the CPU and memory, through a tool called CodeCarbon, which turns hardware energy into a carbon estimate. To convert energy into emissions, we use Indonesia's grid intensity of about 0.676 kilograms of CO2, equivalent per kilowatt hour, since that reflects where this system would realistically run. One important fairness detail: we cap MongoDB's WiredTiger cache at 30 gigabytes, which is nearly all of the machine's RAM, so MongoDB is given every reasonable advantage rather than being handicapped. The software stack in the table pins exact versions: PostgreSQL 15 with TimescaleDB, MongoDB 7, Python 3.14, CodeCarbon 3.2.6, so the whole thing is reproducible. We report constant power rate estimates per resolution and measure the totals for each phase directly. With the setup established, let's turn to what we actually found, the results. This table is the compact summary of everything, and there's a real story hidden in these numbers. Look first at insert throughput. At 1080p, MongoDB is dramatically faster, 337 rows per second versus PostgreSQL's 87, and it stays ahead at 1440p too. But watch what happens as the images grow. Somewhere between 1440p and 4K, there's a crossover, and by 4K and 5K, PostgreSQL is the faster writer, while MongoDB collapses down to under 8 rows per second at 5K. Retrieval tells a cleaner story. MongoDB reads faster everywhere because the image sits right next to its metadata. Now look at the rightmost columns, storage amplification, because this is the punchline that explains the write behavior. PostgreSQL stays essentially flat at about 1.04 times the raw size across every resolution, thanks to its out-of-line design. MongoDB, by contrast, diverges badly, climbing all the way to 3 times the raw payload at 5K. That storage blowup is exactly what drags MongoDB's write speed into the ground on the large images. And as we'll see, it also drives the carbon. This chart makes the insert crossover visual, and I think it's the single most important picture in the talk. Following the 2 lines from left to right, MongoDB starts way up high, winning by 3.85 times at 1080p and still 2.57 times at 1440p, but then it plunges steeply. PostgreSQL, meanwhile, declines gently and almost linearly. The 2 lines cross right around 4K. And beyond that point, PostgreSQL is on top. The reason is mechanical. As the BSON documents grow to several megabytes each, they start stressing WiredTiger's B-tree write path, because MongoDB is trying to shove multi-megabyte blobs through a structure that was optimized for smaller documents. PostgreSQL sidesteps this entirely by keeping images out of the main table. So the lesson from this slide is that there is no single fastest engine for writes. It genuinely depends on how big your images are. Retrieval, by contrast, has no crossover at all. MongoDB wins across the board, and this chart shows why. Both lines climb as resolution rises, since bigger images simply take longer to read, but the MongoDB line sits consistently below PostgreSQL's, meaning lower latency everywhere, roughly 1.7 to 2.9 times faster. The mechanism is the mirror image of the write story. Because MongoDB co-locates the image in line with its metadata, one lookup fetches everything in a single place. PostgreSQL has to do more work. It finds a row, then follows the toast pointer out to a secondary table to reassemble the image. That extra hop is cheap for small images, but adds up across 2,000 rows of large ones. So the very inline design that hurts MongoDB on writes is exactly what helps it on reads. A clean illustration of an engineering trade-off with no free lunch. Now let's put energy and carbon front and center, because that's the whole point of the study. This table breaks down, for each resolution, the wall clock duration, the energy in microwatt hours, and then how that energy splits between CPU and RAM, ending in the estimated emissions in milligrams of CO2 equivalent. Follow the bottom row, the totals. PostgreSQL comes in at 18,439 milligrams of CO2 equivalent, while MongoDB comes in at 20,891. So PostgreSQL holds a 13.3% overall carbon advantage. Notice that CPU dominates the energy in both engines, and that the gap between the two really opens up at the top two resolutions. At 5K, MongoDB burns 12,252 microwatt hours to PostgreSQL's 8281 on that row's energy figure. The green highlighting marks the lower carbon engine per row, and you can literally watch the advantage flip from MongoDB at the small resolutions to PostgreSQL at the large ones. So overall, if you weight all resolutions equally, relational storage is the greener choice here. But that headline hides a more nuanced pattern. This stack chart unpacks that nuance by separating carbon into insert and retrieval contributions. At the two lower resolutions, 1080p and 1440p, the MongoDB bars are shorter. It's greener there simply because it finishes the work so much faster, and time spent running is energy consumed. But as we move to 4K and 5K, the picture inverts and MongoDB's bars shoot past PostgreSQL's because its write amplification now dominates the total. You can see the insert portion of MongoDB's bar ballooning at high resolution while PostgreSQL's stays comparatively controlled. So the carbon crossover mirrors the performance crossover exactly. MongoDB is greener when images are small, and it can be quick, and PostgreSQL is greener when images are large and MongoDB's right overhead becomes the deciding cost. This is why a blanket recommendation would be misleading. This final results chart ties energy back to duration and shows where the energy actually goes. In both engines, the CPU accounts for roughly 57% of the energy. Computation, not memory, is the main draw. The dashed lines track benchmark duration, and you can see they rise together with energy, confirming that slower runs cost more carbon. The key observation is at the right side. Above 1440p, MongoDB exceeds PostgreSQL on every single component, CPU and RAM alike. Two things are happening at once as we push toward 5K. First, MongoDB is spending more effort serializing those large inline BSON documents. Second, the roughly 29.8 gigabyte 5K dataset is closing in on the 30 gigabyte WiredTiger cache, so cache pressure starts to bite. Together, serialization overhead plus cache pressure explain why MongoDB's energy curve bends sharply upward exactly where PostgreSQL stays measured. So what does all of this mean in practice? Let's move into the discussion and conclusions. Let me pull the mechanism together and translate it into guidance you can actually use. On the mechanism side, MongoDB's costs rise at high resolution because multi-megabyte BSON is written inline through B-tree pages, and snappy compression is essentially defeated by already compressed JPEG data. So amplification climbs from about a tenth up past 3 times, and at 5K the dataset near the 30 gigabyte cache triggers eviction stalls. PostgreSQL stays efficient because Toast keeps images out of line, giving it a compact, resolution-independent write path that holds flat at 1.04 times. From this, we can offer carbon-aware guidelines by resolution. For images up to about 1.5 megabytes, that's 1080p to 1440p, choose MongoDB because it gives faster ingest, faster reads, and lower carbon. For images of roughly 3 megabytes and above, that's 4K, and up, choose PostgreSQL for faster ingest, lower carbon, and that flat amplification. If your workload is read-heavy, MongoDB's 1.7 to 2.9 times faster reads make it attractive. And for sustained high-resolution capture, the honest answer is a hybrid. Keep metadata in the database, but push the images to a dedicated object store like MinIO or Amazon S3. The bottom line is that there is no universal winner. You should choose the engine by your camera resolution. To conclude, let me restate the answer to our research question. Measured end-to-end, MongoDB emitted 20,891 milligrams of CO2, equivalent against PostgreSQL's 18,439, a 13.3% carbon premium for MongoDB overall, driven mainly by the 4K and 5K profiles. Per resolution, though, MongoDB is greener up to 1440p, while PostgreSQL is greener at 4K and beyond. And MongoDB keeps its 1.7 to 2.9 times retrieval advantage throughout. We're honest about the threats to validity. This was a single host. The per-resolution figures are constant power rate estimates, and we used a 30-gigabyte WiredTiger cache. For future work, we want to test the hybrid metadata plus object store design, PostgreSQL large objects, 6K and video payloads, and distributed deployments. The takeaway is simple. For green IoT, database selection should be both resolution-aware and carbon-aware. That brings me to the end. Thank you very much for your attention. I'd be happy to take your questions and discuss any of this further.